This question 29 is a little bit of everything good about all this stoichiometry. We're going to need to write a balanced equation. We're going to need to figure out limiting excess, theoretical yield, percent yield. This is the type of question that you could find at the end of a summative assessment. Everything is right here. Now, step one, before I can really do any work with this, is that I need a balanced equation. So if I put this down, like step one is we need a balanced equation. All right, well, this is one of the equations that they've kind of mentioned throughout the unit. I have 15 grams of nitrogen that react with 15 grams of hydrogen, and 10.5 grams of ammonia are produced. Well, I don't care about the amounts right now. I just need the balanced equation. The nitrogen really is N2. It's diatomic, and so is the hydrogen. It's H2, diatomic. And ammonia is NH3. All right, now you don't have to know the formula of ammonia off your head, but it would be something that's given to you, and then I could write the balanced equation from there. To balance then, I'm going to need 2 nitrogen, and that gives me 6 hydrogen. Boom, 6 hydrogen. All right, step 1, write the balanced equation. Step 2. Eventually, this question says, what is the theoretical yield which I need in order to determine the percent yield? Well, in order to determine the theoretical yield, I need to know, like, how do those 15 gram amounts compare in moles? If I have 15 grams of each reactant, cool, but I want to compare them using the 1:3 mole ratio. Do I have a 1:3 ratio? Or is there something that I have extra of? Is there something that I'm going to run out of? Do I have a limiting reactant? And so I can't do anything with those grams. So we're going to turn them into moles. This will be step 2. Determine the limiting reactant and excess reactant. Okay, so we got to get our grams into moles. We've got 15 grams of nitrogen, so we'll cancel grams and put it into moles. The periodic table tells me the grams, and when it is N2, I'll need to use the mass times 2. So about 14-ish times 2, just a hair over 28. And that mass is for 1 mole. 15 divided by 28.01. Now the original number was 15.0, so I think I'll leave 3 figures. 0.536 moles of N2. Now I need to do the same thing with my hydrogen. 15 grams. I need it out of grams and into moles. The periodic table gives me the mass of a mole. Hydrogen times 2, I'm going to say about 2.02. And that's for 1 mole. 15 divided by 2.02. Whoa, baby. Like 7.43 moles of hydrogen. Holy moly, that's a lot. Okay, so now we're supposed to look at the ratio in the balanced equation and kind of figure out how these moles compare to that 1:3 ratio. Now there is a calculation that you can do to determine limiting and excess, where you pick one and you convert it to the other using that mole ratio. Yeah, but I feel like I'm pretty confident on this one. Okay, so look at this. If I were to do the calculation, fine. You pick moles of one reactant and you compare it to moles of the other. I don't know, let's just say I picked the first one. 0.536 moles of nitrogen. I cancel moles of nitrogen and switch it to moles of the other reactant, hydrogen. We'll plug in the ratio. It's 3:1. So I take my point, 536 times 3. And I'd be looking at about 1.608. And that's moles of hydrogen now. But this would have been moles of nitrogen that cancel, and I'd be at moles of hydrogen. Now, none of these little calculations are crazy difficult. This isn't like rocket science. But the numbers mean something, and it is very methodical, and I have to kind of know, like, what do these numbers mean? Well, these amounts over here, the 15 grams, I turned them into moles. These are what I have. I have a certain amount of nitrogen and hydrogen. I just turn them from grams into moles. This little calculation over here gives me the amount that I need. So I need about 1.6 moles of hydrogen, and I compare that to what I have. And now do you see why this one was kind of obvious? Good night. I have like 7 moles of hydrogen. I need 1.6. I have way extra hydrogen. By far, hydrogen is the excess reactant. So by process of elimination, then I know that the nitrogen must have been limiting. And now, over here, like, I picked moles of nitrogen, but you could have picked either. Pick one reactant and switch it to the other. And that'll tell you the amount that you need, and you compare it to what you have. Now, sometimes this little calculation on the right-hand side might not be necessary, because again, you could just estimate sometimes and use your noggin. That, you know, if I look at the ratio in the balanced equation, I'm supposed to have 3 times as much hydrogen. Well, yeah, I've got way more than that. I might estimate, well, yeah, it's like 0.5 times 3. So yeah, I might need like a little over 1.5 moles of hydrogen. Well, yeah, I got 7. Now on the right-hand side, I officially calculated the exact amount of hydrogen I need, but that might not be necessary. If you get to a point where you can kind of estimate the limiting reactant just by kind of using the ratio in the equation, totally fine. That is totally fine. Often we might be asked to determine the limiting reactant, and then it'll just say, justify your answer. Well, I have to show work for that gram to mole calculation. I'm going to have to convert my grams of each reactant into moles. But then this over here, maybe I don't need to always do that calculation. I could just write a sentence, and by justifying my answer, I could just explain. Well, yeah, I looked at the amounts that I have and the ratio in the equation. I need 3 times as much hydrogen, but I've got way more. So then I know that my hydrogen is well in excess. So then nitrogen is limiting. That is enough to justify the limiting reactant. Sometimes you might not need that yellow calculation. You need the conversion from grams to moles, though. All right, so now all of that work gets me to step 3. Calculate the theoretical yield using the limiting reactant. Get out of there. All right, I feel like I can do that. Okay, so I'm going to use the limiting reactant, which is my nitrogen. And eventually now, I want to do this conversion where I go from my limiting reactant to the amount of product. how much ammonia should I produce? Well, I can actually take a little shortcut because I already converted that 15 grams of nitrogen into moles, which I need in order to use that 1:2 mole ratio in the balanced equation. So you can take a little shortcut here and just start her right away with that 0.536 moles of nitrogen. Why not? Because now I can convert over to the ammonia right away. I can cancel moles of nitrogen and switch it to moles of my product. I'll plug in the mole ratio, 2:1. Now I would be at moles of NH3. However, I was given an actual yield of 10.5 grams of ammonia. And in order to do percent yield, I need my actual and theoretical to be the same unit. You could do percent yield with moles, but either way, I'm going to need them to be the same. So let's just tack on one more. Often we'll say, well, let's just turn this theoretical yield into grams. I want grams. I can get the mass on my periodic table. A little over 14 for my nitrogen, plus 3 times the hydrogen. So maybe about 17.04, and that mass is for 1 mole. Plug it in, and I've got my theoretical yield. So we'll say 0.536 times 2 times 17.04. Fantastic. About 18.3. This is a lot of work, huh? That's why this would be like the last problem on a summative, and this would be like a multi-point problem. All right, I got the theoretical yield. I'm almost done. Okay, so then finally step 4 would be to calculate the percent yield. All right, we can do this. We're almost there. The percent yield is actual over theoretical, which the actual will be given. The theoretical is calculated times 100. We'll just plug in our data. Oh, let's see here. My actual yield was given to me. That's the 10.5 grams of ammonia. And the theoretical is that 18.3. Now, they should always be somewhat in the ballpark. Now, obviously, my actual is a little bit less than the theoretical. But if I would have calculated an actual yield that was like 100, and then I see, whoa, the theoretical was 100, the actual was 10, that's either something wrong with my calculation or terrible data. Most likely, something wrong with my calculation. 10.5 divided by 18.3 times 100 gives me about a 57.4% yield. Now, sometimes it is typical that a percent yield with a gas would be a little bit lower. Gases can escape from any little opening in your reaction vessel, your reaction container. So it's kind of hard to contain all of the gas particles that are produced. So that's kind of typical. And here you have it. This is like the entire unit all in one problem. So if there's anything here, any part of this where you're just like, oh man, I can't do that, then now would be a great time to reach out so that we can do a little extra practice.